to welcome all of you to Paris, the center of gravity of the genius from the beginning and now in this meeting that we have the best. So I would like to start by telling you that the nature has stimulated the human thoughts and invention before recorded time. So I would like to start with from the Persian poet Maulana, that he wrote, "Look inside the tiniest particle, you will find universe inside." So let's to see the tiniest particle atom. Nature provides us a full assortment of atoms in the periodic table. These atoms are building block of all matters and works hands in hand with their partner, photon, a piece of light, to communicate energy from one atom to another. When nature combine the atom together, the combination provides nature a rich palette of color to decorate the world around us, also giving rise to the functional complexity of nature. The wing of a butterfly, the feather of a peacock, the sheen of a pearl, all are examples of photonic crystal, nano-structure arrangement of atoms that capture and recast the color of rainbow with iridescent beauty. Each atom with the different electronic structure creates light with the different color or energy when oscillating, from gamma ray, X-ray, ultraviolet, visible, infrared, terahertz, and beyond. But our eyes can see only a small part of this electromagnetic spectrum, the color of rainbow. To see beyond the different color and capture or the create the different color across the whole spectrum requires first the profound understanding of the structure of atom through quantum mechanics. And as Niels Bohr mentioned, anyone who is not shocked by quantum theory has not understood it. And a kind of material called semiconductor, the heart of all modern quantum electronic and photonic. To see beyond the visible light, scientists have invented artificial eyes, such as infrared camera. However, there still exists frontier within invisible light spectra that we cannot yet detect. To both see or shine light in any wavelength range requires a team of scientists to invent new material, new physics, new model, new material and new devices. That's what the objective of this conference is, to investigate the frontier of unseen by having great scientists like all of you, and to come and to give the ideas to better understanding and to be able to see the frontier of unseen. So I would like to start only to say that for this meeting, a little about this meeting that you can see here. My background, first as a Persian, my objective from the very young age, I was curious about the atom, and especially I was doing the neutron activation analysis and the gamma spectroscopy for the trace element in the cigarette and at the center of Persian cigarette and the wine, and to understand the correlation between that, the different atom inside, and the cancer. But unfortunately, one day I had a very high dose of the radioactivity, they forbid me to continue, and they were predicting in 11 years I'm going to have a cancer like Marie Curie and passed away, but I'm still here. So what happens, I went to the physics, and that to do in the best university, of course, University of Paris and Orsay, and with the best professor, Professor Chappell and Lucien Torel, and I tried to do the investigation of the phase transition in lead phosphate, that's a kind of perovskite, and the calculation of the crystal field, and using the paramagnetic ion, such as magnesium, gadolinium, europium, for the exactly with the electron spin resonance for the understanding. But the interesting thing was that it's a very beautiful physics science, and Muller, by the way, he got the Nobel Prize by doing the phase transition. But the problem was everybody was coming asking what is the application. So after my science doctorate, I went to Central Research Lab of Thomson, LCA, that is one of the prestigious, it is not better than Bell Labs, it was equivalent, and for me it was much better. So, and that I went there, and what happens, the first thing, it was the Pierre Leclerc, that some of you that you know, and that the first question that he had from me, it was if I know what is the gallium arsenide, because it was the department of the gallium arsenide. I said something like, say, germanium, because I didn't know. So for me, semiconductor was something like exactly the things that I had at school. And that, after that, asked if I know reactor. Of course, because I worked with the nuclear reactor. He said, no, epitaxy. I said, I don't know anything, but only I know one thing. If there is anything anybody can do, if I like, I can do better. So that it was, I went there for 1 month, they insisted, and it was interesting, the first things that I did, it was a study of this semiconductor and the calculation that I did for all of the 3-part semiconductor, and that it was, they become, and 3 months later, we did the first 1.3 micron laser, and that exactly, as you can see here, that is the first indium-phosphide, gallium-indium arsenide superlative, and that it was, and I'm happy that the Dushman, he is here at the same time, exactly because I started in his lab as an engineer conseil. And what was that? That it was interesting because exactly as you can see in France at Thomson, it was great because we had the opportunity to have the genius student and the postdoc from École Polytechnique, École Normale, and as you can see here, that it was Olivier, that is here, it was my first PhD student that did between the École Polytechnique and the Thomson, and at the same time Martin, that he's here, he was my first postdoc that came from the École Normale, and at the same time my daughter, that now she is at the same time the president of Nanovation, that we started, and as you can see, some of you are familiar with the gold book that I have. We had the visitor, they were coming to visit and to write at the same time, and everybody, and I was bringing to the Madame d'Eugène the restaurant and for to have the dinner, and the beauty it was exactly this genius student and the postdoc and the group, we created the world first everything that it was in the 3-5, and especially for the lasers, 1.3, 1.5 micron, and the detector, the things that it was very important for the telecommunication, changed the world, and the Thales Thomson Central Research Lab, we were only one in the world, and that it was interesting because 1988, it was the meeting of the conference in Japan, as you know exactly. In Japan, the first speaker is very important, and at the same time, to be a kind of, absolutely a kind of out of the norm, it means that to be a woman at the same time. So as you can see here, they put that, the Razeghi from the Thomson, in a keynote address, outlined sheer diversity of potential of MOVP, and we didn't know what that means, MOVP, at the beginning. And with the catalog of first of new material, highest mobility, sharpest interface, new device, and one delegate described as the Madonna of MOVP in her growth south of Paris producing material miracle. Okay, so that is a start. But after 1 year, the interesting thing was everybody, everywhere, they wanted to have me, and that it was in 1990, from SPIE they came to Paris, and at the Thomson, and they asked me to organize a meeting. So that it was a starting, that again I had more than 10 Nobel Prize, and it was the Hollywood of Science, and as you can see here, even they asked for to do the exactly, the German press wanted that the permission to report on the conference, and they did the interview, and at the same time this interview is on the YouTube, and you can hear, but one thing that it was important. Pierre Egran, some of you that you know, Pierre Egran, it was the one that he gave the ideas of semiconductor to make gallium arsenide semiconductor for laser, and his name is in the Guinness Book. He wrote that is very important, that I look at this beautiful conference, similar of this one, but we had much more, and that he said that I was to pursue the topic of semiconductor and their use in optoelectronics. My conclusion is, what my conclusion will be is that in 50 years, at the time, he was 66 years old. So I make without the least fear predictions for 50 years from now, because if they are wrong, I will not be here to hear the laugh about my prediction being stupid. There is still a very good chance that semiconductor will be one of the important bases for optoelectronic products. So today we know that optoelectronic, the semiconductor is basic of everything. And no, I'm not going to the detail. Most of you are physicists, you know that what does mean semiconductor. So I started. But it's very interesting. This book that I organized, and all of that, there were many Nobel Prizes inside, including von Klitzing at the time, and some of them, unfortunately, they are not more in this world, and the Milde Derser-Haas, that unfortunately she's not more there. We thought Milde Derser-Haas mentioned that because they were doing a lot of interview in the press and everything, and she mentioned that is one of the best conference in the world because it was the Hollywood of Science. Like exactly this meeting that we have the best here. So that is the title, and the talk that I gave for the opening at 1990 is exactly the same as is here today, and it's going to be exactly the same in 20, 30, 50 years. It means that the semiconductor and this material that we are discussing, it is, and is continue, the basic, the foundation of all of the science. 3 active component, transistor, detector, emitter, laser. The 3, they are the basic from deep UV up to terahertz, and that, again, as I mentioned, is the foundation. So what happens, it was many different places that they wanted me, but finally at Northwestern, that's just some of you that you know Northwestern, just on the lake, they fill up the lake and they build the building, and they said that if I go there, they are going to give me the last floor of the building. So that it was the important, and that I accepted, and they put at the same time, it's probably our highest, biggest hiring in 20 years, because they wanted to have this kind of activity of the semiconductor science and technology, and they were telling everybody they become or theoretician or computer scientists. They say that I'm only one that I can do, but they cannot have me. So what was the condition that I wanted? And it was interesting because I started by a scratch. It was, and that here that I created the center that is the multidisciplinary and is the real balance. You can do everything that you would like to do, is unique, but what happens, it was interesting because we did the inauguration the 6th June 1993, as you can see with both Leo Ezaki and von Klitzing, but the interesting thing is the following. I would love to see that. It was the 6th of, exactly 6th of the June, that it was Sunday, that von Klitzing, that saying that, like all students of Professor Razeghi's group, we worked at Sunday in the laboratory, the facility is really impressive. And Dushman that is sitting here now, what he would, again, it's impossible to compete against this group that should, we should, we do not continue exactly following. And now the same way, Leo Ezaki with some of my students together, exactly the 6, as you can see, and we had the same title, the same subject that we had the workshop, and we did again the inauguration exactly as you can see, similar to this meeting. And some of my students that you can see here, that the Guillaume Labéry was a student of Albert Ferg that you can see, and one of my students that is the number 24 as a PhD, Steve Slivkan, that he came at the age of the 18 years that he, and now he's just for the moment, he's at Northwestern taking care of the group that when I'm here. So what happens, we did again, that it was here very interesting. Can you, okay, put that here. I would like to see that a small part of this meeting.
The theory of relativity is right. I knew that Professor Razeghi moved with velocity of light, and one of the results of that is that there is time contraction. My speech was supposed to be 40 minutes, then became 30, then became 25, now it is 20. So things are in a relativistic time frame. But I decided to come only to convince Professor Razeghi that I don't hold it against her that she did not come to Bell Labs.
So, as you can see, I'm only one to say no to Bell Labs during, okay, stop that. Okay, and now, what happens after that, not only I created the center, but I created a strong, the educational basis. I created the undergraduate and graduate of solid state engineering, and at the same time with the 4 textbook, that one of the textbook exactly the fundamental of the solid state engineering, 4th edition, just more than 2 million chapters downloaded just immediately after it came out, and the Chinese, they tried to hack it and to put on the online so everybody can use it, thanks God. So, what happens? I'm giving you some of the work that we did and we continue. From the 3-5 semiconductor, and I'm not going to the detail for what, from the deep UV up to TERAS, everything that you can see, it was for the first time to create, and it's continue, and at the same time is important. That the one most important, 890, you have the Nobel Prize, Professor Jalamo is going to speak to say that you need exactly the basic, exactly the source that it was, everybody was using gallium arsenide, gallium aluminum arsenide. And that, due to the problem, the law of Thom was short, and it was a kind of big problem. So I came with the ideas of the quaternary, with exactly the diagram that I showed you, that we demonstrated immediately that we can make very simple, but without aluminium, to use the quaternary gallium arsenide and to have exactly the law of Thom, it becomes infinite, and we can have exact. All of the information is in the one of my book, MOCVD Challenge Volume 2, that I'm not going to get. Now about 1.3, 1.5 micron. That it was with liquid phase epitaxy, and it was the basic of the telecommunication silicon optical fiber. So I make that, again, the first DFE, and at the same time, with the excellent performance that is exactly, that is changed the telecommunication. Now coming to the T5 micron, antimonide base, we came again with the interband antimonide, and to show the result that is inside, again, the book that I'm not going to detail, but in the quantum cascade, that it was the 2 group, my group and the group of the Federico Capasso, that they came, DARPA came to ask me about the interband and the Bell Lab about the intersubband, and that after 3 years that they were doing, unfortunately, they had low power and low temperature. So again, the same program manager, Durvasula and Henry, from that they came to Northwestern and they asked me to be involved. So immediately after that, we started that at the same time, one of my students, undergraduate, David Haydari, that is here, one of the work that he did at the New Year's Eve called me, and he had the 230 watts the result that still is the unique in the world that we're in, and at the same time the terrorists, so that we started. 1997, it was a lot of publicity exactly, and it's continued, and up to now, we have the current world record, and the result is continuing to come out, and that's most of them is the cover of the new, the journal at the same time. Now, coming to the detector, because you cannot have laser without detector, they are connected with each other. Okay, that is not necessary that will go there. So they, again, from the deep UV up to terror, and that exactly, that here, as you can see, indium antimonide, and for all of that, that I'm not going to the detail, only to tell you one thing. The Razeghi gave the ideas of the superlattice gallium antimonide, indium arsenide top 2, and that many different groups in the world, they were working, especially in Germany at the same time, everywhere, but nobody could make the focal planar SV. So they came to me again. I said that, all right, immediately 2003, and we started this material, and for the more, and the Professor Human Mohseni, my number 23 PhD, at the same time, his PhD was starting to do the first, exactly the first course of the top 2 and the demonstration of excellence, but for the focal planar is one of my students, again, that the Yajun, that he came from the physics department, and he didn't know anything, but he has the background. So we did immediately, we made the first focal planaries, and that now he's the big boss at L3, and that one after each other, as you can see, we did the different thing, and everything is transferred to the technology. And my student number 38, now we mean that he was again from Ecole Polytechnique, correct, and now he's the big boss at the HRL that is working. And now what we did again, it was again, we started that the first, again, but that came in and is continue exactly everything is the first or the best, and it's continue. And it is, and it's continue. Again, that is the really, it is the basic. Now, I would like to explain to all of you one thing. On Earth, the ozone atmosphere absorbs strongly the wavelength less than 290 nanometer. So create a kind of the window, solar band window between 240 to 290 nanometer. So the optoelectric component, the lasers and the detector for the short wavelength at this wavelength is very important for the different application above ozone and on Earth. But the most important part, especially at the present time, the deep UV deactivate the DNA of virus, bacteria, pathogen, and destroy their ability to multiply and create disease. And at the same time, the most of this kind of virus, the anthrax or the coronavirus or the tyrosine, they flourish when they are excited by UV light, according to their fluorescence energy. So what happens here, we tried to come to make the T5 aluminum gallium nitride, to make them, and using the sapphire substrate, I'm not going to the detail of that, but we make everything that you can see for the world first. We demonstrated, and one of my students, Danielle Walker, that she's not she's a vice president of Global GE, and that we did, and exactly as you can see, any wavelength for the solar band window with the 4-5, the order of magnitude, the solar band rejection ratio, and that is the norm of the quantum efficiency in the theoretical one. So you can see here, and we put at the same time lateral epitaxial overgrowth, everything that you can see. It was 2013, still they are unique, still they are important, and it's the future again. Now, what we did, we tried to have some the defect engineering. That is the sapphire substrate, and that is the aluminum nitride. Every 9 plane of sapphire is equivalent of the 8 of aluminum nitride. And as you can see, every 9 plane, they have one edge dislocation. That is the perfection So by that, we use that for the both LED and lab, and we created the world first for the biological chemical sensing, 280 nanometer. If you have again anthrax, a small, that is the fluorescence of the anthrax, the fluorescence and the absorption, so that exactly as you can see, all of that, they are the things that we did, again, long time ago, and now it showed that absolutely 280 nanometer, just the Nishio and the Korean, they showed that with the 280 nanometer LED, you can kill more than 99% of coronavirus in less than 1 second on the air and at the same time on the surfaces. So that, as you can see, how it's important. Now, on the other hand, for the lasers, the first blue lasers came 1993 in Nishio, and that it was the Nobel Prize for the Nakamura and Okazaki, but all of the aluminum, so the aluminum gallium nitride is developed at Northwestern in my group, and now here, again, that it was New Year's Eve at 10 p.m. that we got the first blue lasers. And that here, that is two of my students, Patrick, again, it was from the Ecole Polytechnique, and with the social, they get married, now both of them, they are big professors at the University of Alabama. And now, we send that, nobody could believe why, because the multi-billion went to the different company and the group in United States, and nobody could make the laser. So they said that, no, it's not. So that the Bell Labs called me, said that if you send it to us, you're going to give to Nakamura to review that. 1 week later, the scientific quality of this paper is excellent. There is absolutely no doubt that the paper is correct. The reviewers found this paper is a pleasure to read, and the excellent result in blue lasers. So that it was, but it's not finished. As I explained to you, all of that, everything that I did and we are doing in my group, it takes 10, 15, 20 years. The other group, they work, and to come near, but that, just here, Geiger mode at 255 nanometer. That is our new result. On the just, is the unique in the world. Just 2 weeks ago, last week, we had from the MIT Lincoln Lab. So they are asking, and that to have the diode in order to work on that, and we send and my student working at the same time, continuing on that, and the dark current UV, again, aluminum gallium nitride, the cover of the IEEE, all of that is continuing, and again, not only that, because with the top two, similar to the mercury cadmium telluride, we need to have the planar, and that is again the result that is continuing to come, and now, one of the most important parts, I explained to you that UV is very important. But unfortunately, there are always some problem, physics and the scientific problem. So gallium oxide, that is thanks to my daughter again, because that is, she started and she did, her PhD is the high TC superconductivity, but so expert in oxide. So we tried to learn from her, because she was doing with the laser ablation, the LED. Is a laser ablation. So that some of the program manager at the NSF, they called me, they asked me, manager, if you can do that with MOCVD. So we changed it, exactly as you can see, that because that is the polymorph, is the perovskite. So it has the different phase, and that the beta is the high, but is excellent because it's the high power, direct gap, and the very 5 electron volt. So it's very important, especially for the transistor. But not only that, because the Baligo parameter is very important, but it's very, very radiative hardness is very important. So they said that just recently, the detector that they did at Nanovation, it was a subject that went to the SpaceX, they sent on the scope, on the space, and that, so that again, this result, that is very important, and that is future, because there are a lot of physics, a lot of interesting for the phase transition, similar to the work that I did for my PhD for the perovskite, for the lead phosphate. And now, here, again, that is continuing, that is for the lasers. just the quantum cascade laser, high power but non-silicon for the different application, and that's exactly, as you can see, is on the cover of the journal, and is continuing again for the 10 micron, because now, unfortunately, the high power laser, it becomes the ITAR control, and you have to be very careful if you have more than 1 watt in continuous phase. That is a jail, but not, of course, thanks God, not yet for us, and that the most important, the terahertz, that's the frequency come, and that the terahertz, that is the world first, and is great, but it's going to take at least maybe 10, 20 years. If any other group, you know that because they have some of the experts here, they know. So all of that, that is the future, and we did exactly the camera and transferred the set of this result in the space for the space shuttle they are using now to top 2 instead of mercury cadmium telluride. Dr. Mursi has to be here. Unfortunately, he has some problem of the in Paris, so he's not. I believe that he's not here yet. But the problem, because we transfer all of the technology to replace mercury cadmium telluride now with the top 2. So it was the VISTA program. Can you put that VISTA 2 minutes only to understand what does mean VISTA? Only 1 second to see that, okay? Hayop. Hayop, monsieur. Okay, because the VISTA, that is the program that they created in United States for exactly the top 2, but it's ITAR, and it's only the university cannot participate, and it's only the exact, if you cannot put, okay, yeah.
VISTA, an OSD success story, transitioning technology to the warfighter. The United States military has historically maintained a competitive edge in infrared sensor technology and has...
Okay? No, it's on our website, you can see that, but the input, okay, to put the last figure, please. Yes, here, exactly, good. The previous one, yes. Perfect. And that, I would like to see that. That is the government people, because that's not, university is not that to say that. It's true that her students are excellent and make great contribution to VISTA. Most leading DoD contractor participated in VISTA has her student, L3, HRL, that we have that here, the FLIR, the Teledyne, JPL, etc. They all played an important role. In VISTA program, her group's reach is also research is also very impressive, always has a lot of results, and very quickly she's having difficulty working with industry because nobody could keep pace with her, but the impact of her research is significant for the 3 parts. So that in the 20 years, it means that it was in 2012 that they asked that we create the MIOD, the conference at Northwestern, and to have again the 20 years anniversary, that again with the von Klitzen and Lewezaki, and that is exactly the wonder of nanotechnology, that's for the SPOE that is came, and now it was again the 30 years later that they came again exactly to ask me again to organize now for the 30 years. That it was 2019 that with again the Dr. Vinya and the Professor Polmonier, and with exactly the Dr. Terni, we went to see the Institute of Marie Curie. And that is the Laboratoire de Marie Curie at Paris, and we wanted to put that here. But unfortunately, it was the COVID, and we could not. So that, after that, it was the Henri-Jean Drouin, that is not yet there, and he proposed to put that in École Polytechnique, that you saw that you received, he's just arriving. Professor Henri-Jean, we are speaking about you. don't be lazy, please, hurry up. And that, unfortunately, we couldn't. So what happens, that we put that here this year, so it was, again, you have to have von Klitzing and at the same time Razeghi. Razeghi, you have to know that. He is now 99 years old. Since he left IBM, that every year with his wife Masako, that he is at the same time a painter, is an artist, and they are sending the Christmas card. And I'm sure that some of you are receiving. Do you receive any card from Razeghi? The Christmas card? No, but some. Is there anybody that receiving? No, no. Okay. So as you can see, that is for this year, and that it was 2011. As you can see here. So he wished the best, and now he has 99 years old this year. And he gave me now the material that you are going to listen tomorrow. Okay, that with the Professor Mugu, that you are going to have the session, and you are going to hear from him. That is very interesting, because it's inspiring, really. And now what happens, exactly this meeting, objective was, is, and continue. Exactly, understanding of the structure of atom and gene, and that is the thing for the 21st century, that is continuing. So by conclusion, I would like to say that this meeting, again, we have the best, and to thinking about, as Ekran was telling, he mentioned that he became philosopher. It means that to know everything about nothing. That is exactly our cases. More we know, more we have the problem, and we need to solve. And we need the mind, and the people that they have the motivation, they have the curiosity, that they have the passion for to continue. Unfortunately, it's very hard. I'm looking on Professor Henri Jean, that he was doing everything at the same time to send the best student of the Polytechnic, and at the same time, but unfortunately, no, it's very hard. So I'm counting on all of you. By that, I would like to start the meeting with the great scientist and great my professor at the same time, and somebody that not only has passion, and the great at the same time, the professor, great scientist, and to hear about not only his Nobel Prize for many different things that he did, especially the new work at the same time. So please let to, again, to welcome Professor Gérard Moreau, please.